In this video, I'm going to work through the 2014 pre-response section as well as the other ones in that brief little packet. So if you have any questions on these, just shoot me an email or come by and see me. In 2014, this is one of the early years of the new FRQ, so this is a 4-point FRQ. You'll find these are a little bit easier. The answers will be a little shorter. But just make sure you answer them completely, and that's the key. This question is kind of goofy. They give you the nonmetals, and then they give you formulas of compounds that would form with fluorine. So notice your noble gases here have none. Some binary compounds that form between fluorine and various nonmetals are listed above. A student examines the data and poses the following hypothesis. The number of fluorine atoms that will bond to a nonmetal is always equal to 8 minus the number of valence electrons in the nonmetal atom. You can see that kind of applies here. 4 valence here for carbon, so 8 minus 4 is 4. You get 4 fluorines. For nitrogen, it would be 8 minus 5, so that's 3 fluorines. So this hypothesis is just finding a pattern. So what we're going to do here in part A, based on the student's hypothesis, they just want to see if you can read the instructions apparently, because we're going to do it with chlorine, and so 8 minus chlorine's valence. This whole question part A is just, do you know how many valence electrons are in chlorine? That's what they simply could have asked, and that gives you 1, and that tells you the number of fluorine atoms you can have. So this formula they're looking for is CLF. That's it. In number 2, though, we have a Lewis structure. I told you every year there's going to be a Lewis structure, at least one you have to draw. CLF3 is not a super hard one, but it is one you have to pay attention to. So we're going to add up all of our electrons, 7 for chlorine, 3 times 7 for fluorine, and that gives you 28, so 14 pairs of electrons. So in a central atom here will be the chlorine, because remember the central atom is the least electronegative. Fluorine will virtually always be terminal. Alright, now we start assigning sigma, sigma, sigma. That's 3 shared pairs. Alright, now I've got 11 lone pairs to add. We always start with the terminal atoms. Fill those up so that they all have an octet, and that is 9. So we have 2 left over. Fight the urge to put in double bonds. You always put these in as lone pairs. You don't add double and triple bonds unless this number were 0 and you needed to complete an octet. That's not the case here. I have leftover pairs. They have to go on the central atom. So there's your Lewis structure for CLF3. Alright, and then part C is going to test your understanding of geometry. It says 2 possible shapes are trigonal planar and T-shaped. The student does some research and learns the molecule has a dipole moment. Well, what does that mean? That means it's polar. And so this question is really just asking, do you know which of those geometries would give you polar? So trigonal planar would be this shape here, roughly, where your bond angles are 120 and you only have 3 domains. Well, that's obviously not what we're going to have here, because we do have 5 domains in our Lewis structure. So the T-shape is what we're going to have. Well, heck, I'm not going to redraw it. So the T-shape is what we have here. We've got 2 positions here in the geometry. You've got the axial and the equatorial positions. The lone pairs are going to be in the equatorial position with one of these fluorines, and the other 2 will be in the axial position, so that's kind of forms the T, the arms of the T, and then the other one would be kind of pointing downish in the shape of a T. So if it has a dipole moment, that means it's polar, and of those 2 geometries, we can say the T-shaped geometry is polar because it lacks symmetry. And what we mean by lacking symmetry, and that's enough for you to get points, but I'm just telling you now. What we mean by lacking symmetry is that not all of the dipoles cancel. So this trigonal planar here is nonpolar because if you do a sum of forces on all these different angles here, the fluorines are all pulling, these two are pulling up at the same angle, and that cancels with the one pulling down. This one's pulling to the right, this one's pulling to the left at the same angle, so they cancel. So all your forces cancel here in the trigonal planar. So in the T shape, they do not. They do not cancel at all. You're going to have a dipole moment in the direction of those lone pairs. Alright, and then the last question here. In an attempt to resolve the existence of ClF3, because remember that beats the hypothesis, the student researches compounds that form between halogens and fluorine and assembles the following list. Well, we got our answer to part A here. They didn't put it in the box because they didn't want to give the answer to part A away. And then in part B, we learned that there's also a ClF3. Based on the concepts of atomic structure and periodicity, propose a modification to the student's previous hypothesis to account for compounds that form. So this, I don't really like this question a whole lot. As you can guess, when they tell you to base it on the concepts of atomic structure and periodicity, they're not telling you either or. They're telling you to answer it based on both. So that's unfortunate. The periodicity part of this is pretty easy. So as you go down, the halogens each one can add more. Let's add a larger molecule with more F atoms. That's what they want to see. Fluorine can have just one, chlorine has two, bromine has three, iodine has four. And so that's just, the bigger they get, the more you can have. So that's not too hard. Most of you would have said that. But most students will miss this question on the atomic structure because either they just don't even answer it at all because it's a little harder, or they didn't know to or forgot to. So what we need to say here is to acknowledge the fact that everything here seems to be an odd number. So the fluorine's atoms add in odd numbers, and to me that should be all enough. But looking at the scoring guidelines that year, they wanted you to say something about due to there being an odd number of valence electrons. So to me that's kind of silly and just a little bit superficial, but they didn't email me asking my opinion. Alright. So again, on these 4-point questions, you really, ideally of course, you want to get 4, but really 3 points out of the 4 is really the goal we want to shoot for. So if you didn't get part D because it's goofy questions, worded weird, that's fine. But there's really no excuse for you not getting C, B, and A on this particular question. So if you did, sucks. Alright. So now if you want to hit pause and work 2015, you can. But we're going to go through this. Alright, this is a portion of another 4-pointer, but this is only part A and B, and I believe this is just going to be 2 points out of the 4. I don't remember what the other questions were. But this is about ionic bonding, so this is our lattice stuff. A student learns that ionic compounds have significant covalent character when a cation has a polarizing effect on a large anion. As a result, the student hypothesizes that salts composed of small cations and large anions should have a relatively low melting point. Select two compounds from the table and explain how data support the student's hypothesis. So let's just kind of go through it again. The student says salts composed of small cations and large anions should have low melting points. Well, your job now is to go find something that you can compare that actually has different sized anions. There's a couple of choices to make here, I believe. But the best choice to make would be the lithium iodide and the lithium fluoride. In that choice, you have the same size cation, and what you're doing is you're significantly changing the size of your anion. So in this, the iodide is the largest anion, and the fluoride is the smallest, with two L's. So let's look at the melting points. The iodide definitely has a lower melting point than the fluoride of lithium. So it looks like there's some correlation there. So we can say here that the lithium iodide, has a lower melting point than the lithium fluoride. And then we just want to kind of back it up a little bit. Just acknowledge iodide is much larger than fluoride. So this supports the hypothesis. So that's really it. You don't have to be overly complicated. All right, then B part, identify a compound from the table that can be dissolved in water to produce a basic solution. Write the net ionic equation for that reaction that becomes basic. So this goes back to acids and bases and has very little to do with bonding, but it's a good review nonetheless. So we look at this, our two possibilities here. Well, I guess there's 5 possibilities. So we've got lithium, sodium, potassium, fluoride, and iodide. So those are our 5 possibilities. Hopefully you would eliminate all of your cations immediately, because cations are not basic. Cations are acidic. So really these are your choices. And now I hope you remember that fluoride comes from HF and iodide comes from HI. And we've learned that HI is a strong acid. So in terms of equilibrium, this is a one-way street. HI dissociates into H and I minus, and that's a single arrow. There is no equilibrium here. You will not go back. Iodide cannot go back and reform HI, but HF can. That's a weak acid. And so we do get an equilibrium here. Fluoride can go back and react with water to reform HF. So that's the basis of your explanation here. Fluoride is a weak base so will react, or hydrolyze is the better word, with water. And here's the equation they asked for. Fluoride plus water goes to HF plus the hydroxide. All right, if you want to hit pause now, before I go over 2016. All right, I don't remember why there's no A here. I don't know if I just skipped it or it wasn't relative to this. Write the complete electron configuration for the sodium ion in the ground state. I remember in 2016 I had a lot of students miss this question, and it's because they weren't thinking. So what a lot of students did that year was write the electron configuration for sodium atom. So they would say 1s2, 2s2, 2p6, and 3s1, 2, 4, 10, 11 electrons. And they left it at that. That is not the same thing as sodium cation. In the cation form, you're going to lose the valence. So you actually need to rewrite this for sodium ion to be 1s2, 2s2, 2p6, which is uncomfortable because in pre-AP we just didn't do that a lot with ions. But it's a thing. And so maybe you're wondering, could you use noble gas configuration? The answer is yes, but you could not answer this as neon in brackets. That's a no-no. You could have answered this one as helium 2s2 2p6. That would have been okay. Nope, it would not be okay, because I just read the question. It said write the complete. I just noticed that. Don't make that mistake. That would be terrible. So it had to be this. All right. Using principles of atomic structure, explain why the sodium ion is larger than lithium. Okay. Don't overcomplicate that. We know that cations are going to shrink, and the more positive they are, the smaller they're going to be. But that really doesn't affect these two because they are in the same column. So this is really just due to sodium. Even the cation has more electrons, so they occupy more energy levels. And to ensure that you get the full point, what I would do is I would just write the electron configuration for both, because anytime you answer a question, you really want to demonstrate that you really want to discuss both. And so we've already got sodium right above it there. So you can see here we're using very specifically the second energy level for sodium, and that's further away from the nucleus. It wasn't really important that it was a cation. If this would have been sodium atom and lithium atom, the answer would have been the same. Which salt, lithium chloride or sodium chloride, has the greater lattice enthalpy? All right, we don't have a lot of room here, so I may come out here and answer that. So this is all about Coulomb's law. Remember, the two factors that we reviewed that affect lattice energies is going to be the size of the ions and the charge of the ions. In each of these, you've got chloride, so chloride is not really going to change anything. Both of them have chloride. So really it comes down to the lithium or the sodium. So we're just going to answer that with Coulomb's law. According to Coulomb's law, energy is inversely proportional to the distance between the ions. So since lithium is smaller, the bond length is shorter, thus the energy, or enthalpy if you want to use enthalpy, is greater. And I would just show the graders that I know this. The radius of lithium is less than the radius of sodium. You don't have to answer everything in complete sentences. You can put all the information there in little chunks. Just make sure it's sort of organized and flows. Alright, so in E-part, I pointed this one out in class. We've got a lattice here. It says identify the ions by writing the appropriate formulas in the boxes. So remember, this is all about size, cation versus anion. We know that cations get smaller, so this is your lithium here, and the bigger one will be your chloride, your anion. And then in F, the lattice enthalpy of lithium chloride is positive, indicating that it takes energy to break ions apart. Yeah, so that's basically all bonds. However, the dissolution of sodium chloride in water is an exothermic process. Identify all particle-particle interactions that contribute significantly to the dissolution process being exothermic. For each interaction, include the particles that interact and the specific type. So this is kind of that Born-Haber cycle. No, it's not. It could be. It's part of it. It's not the whole thing. So let's talk about the dissolution process. So we start out being in the lattice. So we have to overcome ionic bonds. Broken. And then in the water, so that's a solid, we have attractions between the ions and water. So we're going to have ion dipole forces added. Alright, so now it's just a matter of putting this into words. So we're going to have to put energy in to break the ionic bonds between lithium and chloride. And then we're going to get energy back by forming ion dipole forces between lithium cations and water and chlorides and water. And so if the overall process is exothermic, that means we have way more of these and in greater total energy than it takes to break the ionic bond. Well, that's a confusing little addition there. Alright, so if you want to hit pause before we go over that one, hit it now. Alright, so more Lewis structure type stuff. So just come out to the side, we got 2 times 6, 2 times 7, add those up. 12 plus 14 is 26, 13 pairs. Alright, they kind of laid it out here for us, so let's go ahead. We got 2 central atoms, so that's 1, and then 2, 3. That leaves me with 10. So let's fill up the terminal atoms next. So that was 6. And we got 4 left over. Okay, well it just so happens that these could both use 4. And that takes us down to 0. So potentially that's it. I'm just kind of looking at the formal charge here. I think there's a double bond between those sulfurs, but I don't think we need it. So that would be good enough. Remember, you never double bond halogens when they're terminal. Never, never. In part 2, what is the appropriate value of the chlorine-sulfur bond angle? Yeah, I know that's crazy. So what they're asking you is, what's the bond angle around that sulfur? Because that's in the middle for that one. So we need to go through the geometries here, and really all you need to identify is the electron domain. So this has 1, 2, 3, 4. Even if it was a double or triple bond, this would still be 4 domains. So this is going to be tetrahedral. Electronic geometry, not the molecular. The molecular geometry is bent. So the bond angles on that geometry will be approximately 109.5. And it'll be a little less, but approximately. That's what they want to see. Do you know tetrahedrons are 109.5 and not 90 degrees? And definitely not 180 here. Alright, D part. Carbon tetrachloride can also be produced by reacting chloroform with chlorine. as represented by the equation shown here. At the completion of the reaction, a chemist successfully separates carbon tetrachloride from hydrogen chloride gas by cooling the mixture to 70 degrees, at which temperature the carbon tetrachloride condenses while HCl remains in the gaseous state. Alright, so they asked this question involving HCl and intermolecular forces a lot. Not always with carbon tetrachloride, but HCl is very common. Identify all types of IMFs in HCl. So what you have to recognize, if you don't just know it off the top of your head, is what the structure looks like of HCl. And it's a binary compound, so technically you just subtract the electronegativity differences, but it's polar. We've talked about that a lot. So polar, your IMFs to be London dispersion, because they are in everything, and then dipole-dipole. And they asked that one a lot because the casual student would see that hydrogen there and add hydrogen bonding, but that is not the case. There is no hydrogen bonding with chlorine. What can be inferred about the relative strengths of the IMFs in carbon tetrachloride and HCl? Justify your answer in terms of the information above. So very important. So just state the obvious. That's all they really want you to do. CCl4 condenses first. And now for you, what does that mean about its IMFs? Does that mean they're stronger or are they weaker? Well, if it condenses first, it comes out of the gas phase into liquid. Liquids have more IMFs, so CCl4 must have stronger total IMFs. And that's it. It doesn't even ask you what they are. I mean, it turns out CCl4 is nonpolar, so it only has dispersion forces, whereas HCl has these two we listed here. So most people would say HCl has stronger IMFs because it's polar. And this is a case where the polarizability of CCl4 definitely overcomes the dipole-dipole, or the lack of dipole-dipole that it has. Alright, we're almost done here. Last one. Hit pause if you want to go over the 2017 first before I do. Alright, so we got the isomers fulminic acid and isocyanic acid. So you can see real quickly the difference is, instead of a triple bond between the carbon and nitrogen, we've broken that up into two double bonds, which means the carbon has to have a lone pair. And carbon hates having a lone pair. Explain on the diagram on the left is the better representation for bonding in fulminic acid. So there's several ways to answer this, but they did tell you justify your choice based on formal charge. Okay, I'm going to take it to the top of the page just to make it a little bigger and easier to read, because I know some of you don't remember formal charge at all. So in formal charge, we take the valence electrons 1, 4, 5, 6, and you subtract from each atom the number of electrons assigned to it in the structure. So here hydrogen just has the 1. So 1 minus 1 is 0. Hydrogen's in good shape. The carbon here has 1, 2, 3, 4. Carbon's in good shape. The nitrogen has 1, 2, 3, 4. So the nitrogen's a +1, not the end of the world, but not as perfect as 0. And then for the oxygen here, it's 7. 1, 2, 3, 4, 5, 6, and 7. So that's a -1. Now what does that mean? Well, it's okay. The 1s are okay. And this is a neutral compound. This isn't an ion. So these two add up to equal 0. Essentially what it tells you is where the dipole is in this molecule. The oxygen is where the negative charge is going to be. This nitrogen atom here in the formula has a slight positive charge to it, slightly polar positive. And that's really all it means. So this is doable. Let's do the same calculations over here. 1, 4, 5, 6. The hydrogen hasn't changed. It's still 0. Now the carbon is going to be 4 minus 1, 2, 3, 4, 5. Well, yeesh. -1. Not the end of the world yet, but it will be. The nitrogen here is 1, 2, 3, 4. So that's a +1. And the oxygen here is 1, 2, 3, 4, 5, 6. So that's a 0. So the oxygen actually is better in this second structure. Nitrogen's the same, but the carbon's different. So this isn't the easiest answer to unpack unless you really understand what formal charges tell you. In the first structure on the left here, the -1 was with oxygen. And that's okay. That makes a lot of sense. Oxygen is the most electronegative element in that formula. The fact that it's negative is cool. But over here, why on earth would carbon, which is the second least electronegative element in this formula, why on earth would it want to be -1? What impulse would make the electrons go to that next to last most electronegative element? It needs to be over here with the oxygen. That's what makes the most sense. Even the nitrogen here, how can nitrogen be positive when carbon's negative? Nitrogen's more electronegative. So it doesn't make sense. So I would say here the better representation is the left. Let's just say the left. I was seeing if they had a name for that one. So the leftmost structure shows formal charges, and you word it in a couple different ways here. I'm going to say here that best align with the electronegativities. And I would of course show the work as part of that. Alright, let's see what we've got here in the next part. Fulminic acid can convert to isocyanic acid according to the equation below. Alright, we've got an equilibrium, fulminic and isocyanic. Alright, we've got a couple of Lewis structures. So the one on the left up there was the fulminic acid, and isocyanic is basically just changing the positions of the C and the N. Using the Lewis dot diagrams of fulminic acid and isocyanic above and the table of average bond enthalpies below, determine the value of the enthalpy for the reaction of HCNO to form HNCO. That sucks. That's going to require a calculator. Alright, so remember when we use bond enthalpies, the formula for the enthalpy over the overall reaction is going to be bonds broken minus bonds formed. That's the sum of each. So in other words, the enthalpy for this is reactants minus products. It's virtually the only time we ever do reactants minus products. All the other thermo stuff is products minus reactants. Alright, so there's really nothing to do but do it here. So what are we breaking? There's 1 mole of each. That's the good news. So we're breaking an HC bond. So let's just do this. Let's just do breaking. We've got an HC, so that's 413 kilojoules per mole. We've got a carbon-nitrogen triple bond, so that's 891. Again, all these are 1 mole according to the formula up here, so I'm just counting my bonds. And we're breaking an NO, so 201. Alright, let's add those up. 413 plus 891 plus 201. So if I added those up correctly, that's 1,505 kilojoules to break the fulminic acid up. So now to form, we are going to form an HN bond, so that's 391, a carbon-nitrogen double bond, 615, and a carbon-oxygen double bond, 745. And that is 1751 kilojoules. So our enthalpy here is just going to be reactants, bonds broken, minus products, bonds formed. 1751, and we are going to get a negative number here. Negative 246 kilojoules per mole of reaction. A student claims that the entropy for the reaction is close to zero. Explain why the student's claim is accurate. Well, it probably won't be exactly zero because the degrees of freedom inside the molecule is a little different with those lone pairs of electrons, but for the most part, they're telling you that the claim is accurate. So what we really need to focus on here is that the moles of gas stays constant, and then you could say the number of bonds stays constant. The bonds aren't the same, but the number of bonds, there's 3 of each, stays constant. And the elements involved stay constant. And that's enough. I don't know if just one of those would give it to you, like the moles of gas stays constant. That's the obvious answer. I don't know if that would get you the full credit. So if it were me, I would put something else I'm confident of. And maybe 2 of them would give you credit for sure. I bet you wouldn't need all 3 of these. Alright, D part. Which species, fulminic acid or isocyanic acid, is present in higher concentration at equilibrium? Justify your answer in terms of thermodynamic favorability and the equilibrium constant. Well, we know that favorability is our delta G, and we know that it's related to enthalpy and entropy. So we just got through talking about the entropy term is close to zero. So for this particular problem, the free energy is going to be related to your enthalpy. So that's enough to show that. And then since delta G is only or mostly dependent on enthalpy for this reaction, since delta H is negative, delta G is negative. And I'm out of space, but you can put there negative delta G means spontaneous. Now it did say the equilibrium constant. So a negative delta G gives a greater than 0 value for K. And you can prove that with just saying this equation, negative Nifty. No, that's not the right equation. Sorry. Delta G standard equals negative RT log of K. And then finally, the ammonium salt of isocyanic acid is a product of the decomposition of urea. I don't think there's a question here. Nope, there's not. So that was just a teaser. Tune in next time when we find the rest of that question. All right, got any questions on that first sample? Shoot me an email.